Hello and welcome. Last time I introduced you to the new option in Unity to create synthetic data to train neural nets. And I asked myself, is there anything meaningful I can do with this new option? So I came up with the question, is it possible to train a neural net purely on synthetic images and then classify real-world images on this neural net? So I used Blender and Unity to create a huge synthetic image data set of dice. I trained a neural net on it and checked what happened if I feed real-world images of dice into the system. But this kind of experiment would not have been possible for me in the past because I couldn't create that kind of data set. So before I get into my experiment and the results, I would like to talk about democratizing deep learning, why it's important, and which role synthetic data play in it. Democratizing means that more people get access to the powerful tool of deep learning, and a lot has already happened in this regard. For instance, anywhere in the world you have access to cloud computing resources, especially GPUs, to train your neural net. Basically, all software libraries that are required are freely accessible and open source. And there are tons of excellent training materials to get into the field of deep learning. But there's the fourth pillar that's required for deep learning, and that's data. And as you know, many deep learning systems require a lot of data for training. And if you want to solve a problem for your company, you need your own data. If you only want to get into the field of deep learning, there are tons of freely available data sets that you can play around and train your systems on. But both types of data sets, whether it's your own or one you downloaded from the internet, has a severe limitation. You train a neural net on your data set and then you bring it into production. But only from the training data, you're not able to tell how the system will behave when it's exposed to data points it hasn't seen before. And why is this so important? Because neural nets are typically very sensitive to data points that lie outside the range it has seen during training time. So the people that deploy deep learning systems need a very deep understanding of these severe limitations. And synthetic data is one means of getting a deeper understanding of these limitations and to mitigate the risk of system failing in production. And in any production system, at some point in time, the neural net will be exposed to data points it hasn't seen before. So especially in the area of self-driving cars, using synthetic training data has been a long time practice already. But now it's available to a much broader audience. And that means you can not only cover the edge cases for your own training data and create synthetic data points for that, but you can also ask and answer questions you couldn't ask before. And over time, this will lead to a much deeper understanding of the behavior of neural nets because more people can now do their own experiments and figure out what works and what doesn't work. So let me now get into some details about how I ran my experiment using images of dice.
So first question, why have chosen dice? On the one hand side, dice are simple objects and it's easy for me to create real-world images under a variety of conditions. But on the other hand, dice expose an inherent complexity. They are 3D objects and only the number that's shown on top counts. So the system has to learn the difference between numbers shown on top and on the sides, which also might be visible on the image depending on the angle. So I use Blender to create 4 different models of my dice, roughly reflecting the dice I've been using for my real-world images. 2 rather edgy dice with smaller and bigger dips, and 2 dice models with rounded corners, also with smaller and bigger dips. So here you see the 4 different models I have imported into Unity, where I'm using the Unity perception package to create my synthetic image data. The images have a size of 200 by 200 pixels, which is sufficient to keep all the important structural information. I've written my own randomizer that selects a model, randomizes the number, the rotation and location of the dice, the angle of the light, position and rotation of the camera, and the dice and background color. I'm able to train a neural net on the synthetic data, and I'm taking 90,000 different images. In the sample you see the variation in the dataset. For instance, different lighting conditions causing different kinds of shadows. Then I take one of the standard models for computer vision, a ResNet 152, and then I train the system for about 3 hours, and you see at the end I have an error rate of about 0.5%. That means in 99.5% the system correctly identifies the number shown by the dice. So here are some of the incorrectly classified dice. For some of them it's even hard for us to get the right number because of the low angle or the lighting conditions. But there are other cases where we can clearly see the correct number and it's not obvious why the system has misclassified them. So now I took this system that was purely trained on synthetic image data and used it to classify my real-world images of dice. And the result is pretty remarkable. I have 60 images per class, so 360 images altogether. And here you see the confusion matrix. On the diagonal of the confusion matrix, you see all the correctly classified images, and on the off-diagonal elements, you see the errors. So already here you see that pretty much all the images have been classified correctly. And the calculated error is less than 3%. So even without using any realistic material in my synthetic image data, I've been able to guide the system to identify the correct structures in the images. So here are the incorrectly classified images, and there's no obvious reason why the system failed. On most of the images we can clearly see which number is up. Why the system fails would require a deeper analysis that's beyond the scope of my experiment. But it proves the point that these systems are very sensitive to minor variations, because in many other cases the system has correctly classified very similar images.
So this experiment worked out quite nicely, but next time I will give you some examples where my own intuition fooled me because the experiment ran different than I expected.